So what we're going to do here is look at some carbon-13 NMR spectra and see if we can interpret them and determine something about our compounds. So the question says, which carbon-13 NMR spectrum is for each of the following compounds? We've got propan-2-ol, propanone and propanoic acid. First thing we need to do is draw the structure of those. So if we remember that prop is our word for 3, and that the AN part of the name tells us that we've got single carbon-carbon bonds, and that the 2-ol part tells us we've got an alcohol group on number 2. We then need to go around making sure that every carbon has 4 bonds. We're going to put on those hydrogens. I'm going to repeat that on our other structures. So prop for 3, AN, meaning single carbon-carbon bonds, ketone, meaning a double bond O in the centre between 2 carbons. Make sure every carbon's got 4 bonds. Prop, 1, 2, 3, AN, single bonds, oic acid, carboxylic acid. Make sure every carbon's got 4 bonds. So we've drawn our structures. The first thing we can do is remember that we've learnt that carbon-13 gives us a peak for every unique carbon environment. So what we can do is look at the first 2 structures and notice that they're symmetrical around the central carbon. And so the 2 exterior carbons in both of these 2 structures are the same as each other, and that the central carbon is unique. Now, these 2 structures aren't going to have identical carbon-13 NMRs. They are just going to both have 2 peaks. They won't be in the same places because their environments are different, even though there's the same number of peaks. But their environments, the type of carbon is different. If we then look at our propanoic acid, we can see that that one isn't symmetrical. So we've got 1, 2, 3 different types of carbon in propanoic acid. So we're going to end up seeing 3 peaks in propanoic acid, which means immediately when we start to try to answer this question, we know that spectrum 1 of these 3 must be propanoic acid because it's the only spectrum we've got with 3 peaks. So I'm going to redraw propanoic acid, and then we're going to do a little bit more of a detailed explanation of why this is propanoic acid, or why this spectra matches up with what we'd expect. So if we just re-sketch what we had 3 different carbon types, and if we look at alongside, I've just snipped out the part of the data sheet that we need, and we start with the what I would call the interesting end of the molecule, the carboxylic acid end of the molecule. Now if we look down at our list, it says that for carboxylic acids or esters we should be getting a peak between 160 and 185, and what we can see quite clearly here is that we've got a peak at 180, and that's our carboxylic acid peak. All 3 peaks here look very similar in size, probably representing the same number of carbons, which would be true given that we've got 3 different carbon types. Our second carbon type here, our orange carbon, is living next door, adjacent to the carboxylic acid, and if we look on our data sheet, we can see that that comes between 20 and 50, and we can see we've got a peak here between 20 and 50. And then our last type, which is just a carbon joined to another carbon chain, 5 to 40, would be this peak here. So our spectra does match up. We have, this is of this type from the data sheet, between delta 5 and 40, our red type, and then we've got this one here being a C that is next to a C double bond O from our data sheet, which is this one between 20 and 50. And then we've got our C double bond O type, our carboxylic acid carbon, which is between 160 and 185. So all data confirms that this is the spectrum of propanoic acid. And then if we move down, I'm just going to rub out the highlighting on this one for a second. If we move down and we take our spectrum with us, and we see, look at our carbon-13 data now and our spectrum 2, what we can see is that we've got a peak between 60 and 70 here, but not a peak between 190 and 220, which would be expecting for propanone. So now that we've got two spectra but we're both expecting two peaks, we might want to approach it in a slightly different way and say, look at where we would expect the peaks to be. Now in propanone, because we've got a ketone, we'd be expecting something between 190 and 220, and then we've got the ones that live next door to acetyl bundo, so between 20 and 50 for the red type. So we'll be looking for a spectrum with those two, whereas on propan-2-ol, we'd be looking for alcohol ether ester. This one would be 50 to 90. And then the other two would just be ones that are on the end. And so we'd be looking for 5 to 40s for the red type. So if we look down at our spectra, it looks like spectrum 2 has the peaks that we were expecting for propan-2-ol, and that spectrum 3 has the types for propanone. So if we just pop a little picture in, we think that this one, and we can then have a look at what we did and see if it matches, that this would be propan-2-ol, because for propan-2-ol, if we remember, we had our red type and our yellow type, our red type on the outside and our yellow type on the middle, and our yellow type being this, 50 to 90, and our red type being just 5 to 40. So this was our red type here, and this was our yellow type, which left spectrum 3 as propanone, and we can just see whether that matches up. So we'd be expecting for propanone our yellow type to be at 190 to 220, and our red type this time to be 20 to 50, which we have got. So all matches up, and we've managed to link each spectra to each of the compounds.